It's a very inclusive title. Let me start by thanking the organizers. There are many organizers of this nice program and also of this nice workshop, and it's a pleasure to be here. So I was asked to talk about connections with other areas of mathematics. I assume this is Isaac Newton, right? I mean, so yeah, I'm quite moved by him, but he's not looking at me, he's looking at you, if you notice. But by the way, Newton, I'm told that he appreciated his theological work more than his mathematical and physical work. And in the Hebrew University of Jerusalem, we have the original theological manuscripts of Isaac Newton, so you are welcome to have a look. Okay, so So I would like to start by saying that you know, it is kind of it's very natural to relate various areas of mathematics with groups. For example, because you know, whenever you have a structure, you have a group of automorphisms, you know, preserving the structure. So you can have all kinds of, you know, covering groups, and even in model theory, groups appear, etc., etc. Almost in any area of mathematics. It is less obvious whether what does group theory gains in return, and how do other areas contribute to it. But there are many, many examples, and I would like to discuss some of them. So basically, I want to talk about Lie methods, about contribution of Lie algebras to some problems in groups. I would like to talk about contributions of probabilistic approach and probabilistic methods to groups. Character methods, which is really kind of much in line with this program. Representation theory and how it helps, and also a little bit about applications of number theory and algebraic geometry to group theory. So it's a little bit ambitious. We'll see if we have time for everything. I'm told that this green is hardly seen, and there is a good reason, because we will hardly do algebraic geometry. Okay, so Lie methods. Now, of course, you know, Lie algebras and Lie groups are interrelated, and it goes without saying that, you know, there are strong connections. But can we use Lie algebra to study abstract groups and finite groups in particular? So the answer is yes, and let me give you some examples of these. Start with an nilpotent group. It can be finite or infinite, and GI is a lower central series. Now we can form the so-called graded Lie ring. I think Magnus and maybe also Witt dealt with it. So the Lie ring of G is a direct sum of these quotients of the successive quotients of the lower central series. And you know, these are abelian groups, so you can use the group multiplication to define addition here. And essentially the Lie product is induced by commutation. So you first define it on homogeneous elements. Elements of this are homogeneous, and then you extend by additivity to every element. So you easily construct a graded Lie ring. Sometimes it's a Lie algebra over a field, sometimes not. Now G, in case G is finite, G and LG obviously have the same size, and they have obviously they have the same nilpotency class, so this is very useful. And there is a whole bunch of problems in group theory which were solved using these Lie ring methods, and we don't have any other solution. So let me give you some examples. Okay, so maybe the most celebrated example is a restricted Burnside problem solved by Yefim Zelmanov. Of course, there is a long history here. So the question is, if you have a finite group with d generators and exponent n, so x to the n is an identity of the group, is the order of the group bounded in terms of these two parameters? This is a very difficult problem, and there is a famous Hall-Higman reduction to P groups. Using some assumptions, the classification didn't exist at that time, but it was a Schreier conjecture, and also the fact that there are finitely many finite simple group of a given exponent. So the assumptions of the reduction followed later from the classification. But then research focused on finite P groups, and one advantage of them is they are nilpotent, so you can form the Lie ring in the way I described. Kostrikin made a breakthrough for exponent P, so he solved the restricted Burnside problem for exponent P, and the main tool is indeed this graded Lie ring. Already Magnus, I think, observed that it satisfies the P-1 angle condition. Namely, if you take in the Lie algebra, you have the adjoint operation. So if you take add x and you raise it to the power P-1, you always get 0. This follows from the fact that the exponent is P. And Kostrikin then showed that the nilpotency class of P-1 angle Lie algebra is bounded in terms of its number of generators and this P. And I forgot to say, but the number of generators in this case is the same as the number of generators of the P group. Okay, so LG and G are quite similar, but LG is kind of a linear structure, and it's much easier to work with. Not that Kostrikin proof is easy. I mean, I met a person who told me that he thinks he's the only one who read and understood the full proof. There is a book by Kostrikin which is called Around Burnside. But anyway, by proving this difficult Lie theoretic result, then it is easy to deduce that the order of the group, which is exactly the size of the Lie algebra, is bounded in terms of the number of generators and the exponent P. So that was a major step forward. And of course, the next step, full solution, was by Zelmanov around 1990, and he was awarded the Fields Medal for it in 94 in Zurich. And so the result is that it's true for all prime powers, and therefore by the reduction and by the classification, it's true for all n. So we have a positive answer to the restricted Burnside problem. Okay, so let's see some other examples of the Lie ring method. So Graham-Higman proved that if you have a nilpotent group with sometimes some people say there are many theorems in mathematics about the existence of fixed points or the non-existence of fixed point free automorphisms. In group theory, you cannot have a fixed point free automorphisms because one goes to one, unfortunately. But let's say that this is the only fixed point. So if we have an nilpotent group with the automorphism of prime order P and only one fixed point, the identity, then the nilpotency class of the group is bounded in terms of P. Higman called this function Kp. He was modest, but immediately it became Hp. Now the proof strategy is as follows. First, he proves that a Lie ring with such an automorphism is nilpotent. You see, here you don't have to assume that. Here you assume that the group is nilpotent, that you want to bound the class. But for Lie ring, he proved that, from the mere existence of such an automorphism with only one fixed point, 0 in this case, has an nilpotency class which is bounded in terms of this P, and then he applied it in an obvious way to deduce that the nilpotency class of G is bounded in terms of P. His proof is not effective. It doesn't give us any bound on the function HP. And then there were more developments. John Thompson, well, this is not related, of course, to the Leering method, but it's a major result which I think also solves the conjecture of Burnside. Am I right that, okay, what he proves that a finite group with automorphism, a finite group with an automorphism which with only one fixed point, which is of prime order, is nilpotent. And I think this was already conjectured by Burnside, and this was more or less the PhD thesis of Thompson. It's a very complicated proof. It's a very brilliant start of a long mathematical career. But there was a question about bounds. You know, I'm now skipping to. You see, now this means that if the group is finite, then you don't have to assume it's nilpotent in this theorem, because this is Thompson's theorem. Okay, but then Kreknin and Kostrikin, Kreknin was his PhD thesis, I think, they found effective version of Higmann's theorem. HP is around P to the 2 to the P. Unfortunately, it is far from what people believe. Conjecturally, HP is around P square. So I think something like P square minus 1 over 2 or over 4. So you can take it as a first challenge in coming from this talk. Now, what if you have more than one fixed point? If you have boundedly many fixed points and still an automorphism of order P? So Alperin was mentioned a lot in this conference, so it's good to mention him again. He proved that a P group is an automorphism of order P with P to the m fixed points. Well, you cannot deduce its nilpotent of bounded nilpotency class. I mean, that's just not true. But it's obviously finite P group is solvable, but the solvability length, the derived length, is bounded in terms of these parameters. Okay, so that was Alperin's theorem, and and there was a problem. Can we extend, can we extend this to automorphism of not prime order, but prime power order? And the difficulty here is Alperin also used the Leering method, but the difficulty, but somehow we got around this difficulty. But the difficulty here is that there is no, if you bound the derived length, the solvable length of the Leering, it doesn't mean that the solvable length of the group is bounded. So you have, maybe you can get nice results about Lie algebras, but they don't help you with a group. So so let me mention an old result of mine which solves this problem. So it generalizes Alperin's theorem so that the order of the automorphism doesn't have to be prime. It can be a prime power P to the k. So that's a result, and a consequence which is a little bit counterintuitive is that the derived length of a finite P group is bounded above in terms of the minimal size of a centralizer of the P group. Okay, because of course you can take the inner automorphism conjugation by X, and then of course both the order of X is bounded by the order of the centralizer, and certainly the number of fixed points is exactly the order of the centralizer. So so it shows you that if you have very small centralizers, then the group is in a way close to a billion, because it's solvable of small solvability length. So it's a little bit counterintuitive. Okay, let me tell you a little bit about the strategy of the proof. So we show that the group has bounded rank, so the rank is a maximal number of generators of a subgroup, okay? And then you use, there is a whole theory of p-adic analytic Pro-P groups and the powerful finite P group, which started with Lazar and developed more by Alex Lubotsky and Avinoam Mann. And then you can try to treat G as an approximation, a finite approximation to a p-adic Lie group. And with this in mind, Lazar already defined a Lie algebra of a p-adic Lie group, so you create a finite analog of this Lie algebra, and then you get a new Lie ring, which let's call it Lie G instead of L of G. It's a bit a complicated definition, so I avoid it. And basically, the main advantage of this Lie ring is that it's solvable. Okay. First of all, this is already a theorem of Kreknin, that if you have a Lie ring, you know, with an automorphism of order p to the k with p to the m fixed points, then its solvability, its derived length is bounded. So that was on the shelf already. But the remaining and maybe most important point is to bound the derived length of the group in terms of the derived length of this new Lie ring, and this is the proof strategy. Hugo actually did much more than these theorems. There are all kinds of extensions, and there are 2 books devoted by Hugo devoted to this topic, and various other applications of this Lie ring. Let me very, very briefly mention the very famous Koch-class conjectures by Lidam Green and Neumann. It's about the structure of finite P groups, and it's a long and ambitious project, and many people contributed, including Steve Donkin, who is here, and I wouldn't say there are there are actually different proofs and various approaches, but certainly Lie methods play some role in the proof. Okay, so we are now in probabilistic methods, and I hope you don't have questions, because I don't have time. I mean, you may ask questions later. No, but if you are really uncertain or confused, then do ask. Okay, probabilistic method, well, this will be a bit longer section. So the idea is to prove existence theorems replacing explicit constructions by probabilistic arguments. So you want to prove that that a certain object exists. So usually people just construct it or try to construct it, but sometimes they cannot construct it. Then the idea is to create a certain probability space, and then what you do is you prove that the probability of this property of a random object in this probability space will have the desired properties is maybe tending to 1 or at least bounded away from 0, something like this. And you know, positive probability implies existence somehow. So that's so it is actually a very natural, even naive idea, I would say. But I think that Paul Erdős, it was first Paul Erdős who had this idea in 1941, but you know, it could have, I mean, people in the 19th century did very difficult things. So it is a little bit amazing that it started so late, but of course it flourished, and it started in graph theory and combinatorics, and I think Paul Erdős introduced it to get much better bounds for Ramsey numbers. And so there are here also people from Cambridge and yeah, and okay, so many people contributed to this approach in combinatorics. But what about groups? So what about finite groups? well, let me say that the first existence proof of expanders was probabilistic, so that's an important field in finite group theory. But we are more in line of this conference. We are more interested in finite simple groups. Actually, there are relations between finite simple groups and expanders. And so I was trying to write something about the classification, but you know, there is a first generation proof. I usually impress my students, but writing down some unreliable facts, I'm not sure about the number of pages, but this will be probably a bit more than 5,000. And actually, the third generation approach was discussed here, and it appeared in you know, fusion that talks by radon and fusion system that talk by Ellen, and various people discussed the third generations, and basically let me go back much before the classification, even into the 19th century. There was a conjecture of Netto that two random permutations in Sn generate Sn or An with probability tending to 1 as n tends to infinity. And it took almost 100 years for this conjecture to be proved. It was proved by Dixon. But actually, Dixon relied on quite sophisticated results, 7 papers of Erdős and Turan, which are called some problems in statistical group theory, but they actually tell us a lot about random permutations. So using these tools, this conjecture was proved. And then in the same paper, Dixon, probably some of you know this history, so you can also tell me to, if most of you know, I can just skip it. But, okay, so he made the conjecture for all finite simple groups that in this case they should generate the whole group. So 2 random elements generate a finite simple group with probability tending to 1 as a group order tends to infinity. This was very daring because it was much before the classification, but he had an amazing intuition, and joint work of these people shows that the conjecture holds. Now, something about the methods, because it's much related, for example, to Kolva's talk today and to Martin's talk tomorrow. It is much related to maximal subgroups of finite simple groups, simply because a trivial observation that if you don't generate, then both elements x, y lie in some maximal subgroup. And then this is also something extremely naive. But you can define a certain zeta function summing over the indices of the maximal subgroups to the minus s, say for a real positive number s, and then what I said show that the complementary, the non-generation probability is obviously generated by zeta g of 2. So it remains to show that the sum of gm to the minus 2 goes to 0, and that's how it's done. That's not how it was done in some other cases, in Dixon, for example. But now let's move to some a little bit more challenging problem. So actually, already more than 100 years ago, people were interested in the modular group PSL2Z and finding its quotient, and in particular, its finite quotients and finite simple quotients. So since this group is a free product of C2 and C3, it's equivalent to finding the finite simple groups, which are 2-3 generated, namely generated by an involution and an element of order 3. Well, one family of group which is exceptional is the Suzuki group. You know, all these groups have an involution, but Suzuki groups don't have elements of order 3. So that's an obvious exception. And so there are some long history. You see already in 1901 that most alternating groups are 2-3 generated, and there are various results. And then there is a result of Martin and mine that all all finite simple classical group except PSP4 in characteristic 2 and 3, and finally many others are quotients of PSL to Z. You see, finally many others is not effective. So you can like the probabilistic method, but it doesn't tell you anything about a given group, you know. So I will say something about that also later. But the reason I mentioned this, it's a bit prehistory by now, but there is a probabilistic, of course, there is a probabilistic proof, and essentially what we show is that if we pick around, with some exceptions, if we pick a random involution and a random elements of order 3, then the probabilities that they will generate will tend to 1. It's again related to this zeta function which we defined earlier, and there is also a bit surprising situation when the probability tends to half, which is good enough for them to be quotients of PSL to Z, but it's not randomly 2-3 generated. Now there is a nice result a year later by Frank Lübeck, who is here, and by Günter Mahle, that except the Suzuki group and finally many given other groups, so they give the exceptions, and all exceptional groups are quotients of PSL to Z. That was done with other methods, which applies representation theory and computational group theory. And later there was, there was an ongoing project giving more information about random 2-3 generation, also for exceptional groups. So our theorem before was for classical groups, but actually exceptional groups are also 2-3 generated, except of course the Suzuki group. But I will not say much about it. There is also an extension for RS generation, where RS are arbitrary prime, not both 2. If they are both 2, you know, they will go in a dihedral case. Okay, but let us let me now generalize it to a greater family of group. We discussed actually the modular group. We discussed free product of 2 cyclic groups. These are all particular cases of Fuchsian groups, which are finitely generated non-elementary, namely non-virtually cyclic, discrete group of isometries of the hyperbolic plane. And these groups, they have some well-known presentations, and there is a notion of genus, and maybe surface groups are the most famous examples of Fuchsian groups, but also what's known as hyperbolic triangle groups. I'll say something about them. In a particular case of them is important Hurwitz group, the so-called 2-3-7 group. So there are many interesting examples. And there was a conjecture of Graham-Higman that every Fuchsian group surjects to all large enough alternating groups. So that was proved by, there was progress by many people, and it was proved by Everett in 2000. And Martin and I gave a probabilistic proof, also in non-oriented case. And basically, the idea is to show that if you take a random homomorphism from the Fuchsian group to AN, it will be onto. I'm cheating a little bit, okay. But what about other finite simple groups, not alternating groups? So in this case, a random homomorphism will be onto only in specific, only if the genus is not too small. So it should be genus at least 2 and at least 3 in the non-oriented case. And in this case, we also get random, that random homomorphism to a finite simple group will be onto. So for example, this gives a another proof of Higmann's conjecture, and the proof of this statement. This time we actually need also representation theory, and then we define what we call the Witten zeta function, because he used it without giving it this name. So it's, you know, the sigma of characters degree to the minus s, which is it's a very useful function for many purposes. And the character connections comes from the fact that if you want to count a homomorphism from a Fuchsian group to a finite group, then there are precise formula for the number of homomorphisms, but they involve character values and character degrees. Okay, so that's a character connection. And here is a conjecture which I pose to you, to the audience, which is still very much open. So I think whenever I number conjectures, it means that they are still open. So okay, so for any Fuchsian group gamma, there exists an integer such that a random homomorphism from gamma to a finite simple classical group of rank at least this integer is onto with probability going to 1 as g goes to infinity. So it's not true that there are counterexamples if you don't require large rank, but here we don't know of any counterexamples, and this is still open. I can tell you about some. So it's open in genus at most 1, and I think also at most 2 in the non-oriented case. And a main challenge here are the triangle groups. So here is finally a definition of them. They are generated by 3 elements of given orders, but you also want the product to be 1. So it's quite tricky. And there are hyperbolic triangle groups if you have this inequality. And oh, well, this is a misspelling. So the Hurwitz group is a famous example, and to some extent the most challenging example. And there are many results by Macbeth, PSL2Q quotients of the Hurwitz group. People realized larger and classical groups as quotients of the Hurwitz group. And then there was a new method invented by Michael Larsen, Alex Lubotsky, and Claude Marion, who was a student of Martin. So using deformation theory to study simple quotients of triangle groups, and also some more recent contribution of these people, which gives some instances where we can prove. And the main tool are new character bounds, which will be revisited later. But in general, this is still open. Okay, I'm still in the probabilistic section. Yeah, I don't know what is the probability that I will have time for all the sections, but But there are some nice things in permutation groups which I wanted to discuss, and they gain too from probabilistic thinking. So basis for permutation groups, so probably you know the definition of a base. You have a permutation group on n element as a base is a subset of 1 to n, such that the pointwise stabilizer is trivial, okay? And this means that the action of a group element on a base determines the action on the whole set, and therefore you trivially get that if you have a base of size b, you get this bound. So in particular, so the group order is bounded by the degree n to the minimal base size, which we call bg. Okay. Now, this is important in computational group theory, in getting upper bounds on order of permutation groups, and I suppose, you know, maybe Peter Cameron's talk will be also related, you know, because he's maybe the expert in things like this and relations to the classification. Anyway, so for primitive permutation group, we all know what it is, I guess. There is an Anand-Scott theorem and kind of a related paper by Liebeck, Prager, and Saxel. And actually there was a whole game of finding base sizes for primitive permutation groups, which already goes, you see, to the 19th century. So if you have a primitive group, not AN or SN, then by Bochert the base size is at most n over 2. And then there is an amazing result by Babai, which is almost best possible, but with the classification this is best possible. So the base size, it tends to be small unless we have the whole SN or AN. And now I want to discuss Peter Cameron's conjecture. So he conjectures that if you have a primitive almost simple group, there is a definition of a standard action. So SN and AN on subsets or partition, classical group on subspaces. And in these cases, BG may well be unbounded. But Peter Cameron conjectured in 1990 that in the other cases, the base size is at most 7. That is quite amazing, and I still don't understand how you had this intuition. I mean, some people worked on a weaker conjecture just to have an absolute bound on the base size. But a spoiler, which is probably a spoiler, not a spoiler to many of you, is that this conjecture really holds. And and it is best possible because of the Mathieu group M24. And many people worked on it. I missed some, and some of the approach involved probabilistic methods, and eventually this accumulative work implied proof of Cameron's conjecture. And even, this is the only case where you have base size 7. Otherwise, you have base size at most 6. And also, a random 6 tuple forms a base with probability tends to 1. And also, in many cases, you have actually base size 2. Let me now mention an old conjecture, 1993, I think, of Piber. For many years, there was not much progress on it. Piber conjectured that that there is an absolute constant such that for every finite primitive permutation group of degree n, the base size it's essentially log g over log n times this absolute constant. Okay. Now this bound is best possible because we saw that the order of g is at most n to the base, the minimal base size, so the base size is bounded below by log g over log n. So it would be very nice to have an upper bound of the same kind. And so Piber, it is easy to see that Piber conjectures implies Cameron's conjecture. And there were fascinating developments in recent years. So here is a theorem by Duyan, Halassi, and Marotti from 2018, and they proved Piber's conjecture, even with a specific constant, 45, There is also an additive error term, but this is a very impressive result. And there is a later result by Halassi and Martin and Marotti, where 45 became 2 suddenly. So that's really quite amazing, I think. And the A became 24, and yeah. So I'm not sure, Martin. You didn't use probability, right? Okay. Okay, so forget about this result. Yeah. Okay. Now you see it's a good time to abandon probability and move to representations a little bit and character methods. And Okay, so now we want to discuss complex reducible characters of finite groups, and there are many applications. So, for example, random walks, and if you take a random walk which with a generating set which is a conjugacy class or a conjugacy class and its inverse, then there is a nice character theoretic bound on which leads to bounds on the mixing time. So you want to find t such that after t steps you are quite close to the uniform distribution, and this is in the L1 norm, and this is actually a nice upper bound. So you see that character ratios, these things are very important, and the smaller the character ratios are, you get better results, better upper bounds on the mixing time. So, for example, Diaconis and Shashahani proved that the mixing time of Sn with respect to transposition is roughly half n log n. And you know, Percy Diaconis is also a magician and an artist of cards, and so it also means that 12 shuffles are required to do this. Well, that's a bit another model, but okay. Now, there were all kinds of extensions to other conjugacy classes. Diaconis and Shashahani studied the conjugacy classes of transpositions. So what about other conjugacy classes of symmetric groups? So there are many results by Fomin, Lulov, Igor Pach, Thomas Miller, Jan Christoph Schlage-Puchta. There was a conjecture by Lulov and Pach that if you take a conjugacy class of fixed point free permutation, then the mixing time is at most free. Okay, and in a paper with Michael Larsen, we proved this conjecture. We actually proved some more detailed bounds on the mixing time. So one thing is that the mixing time is bounded as n goes to infinity, if and only if the number of fixed points in the class is at most n to the 1 minus epsilon. And actually the main tool in the proof is to get what we call the exponential character bounds for Sn. So such bounds were actually first proved by Fomin and Lulov in '95, and essentially for special elements. So if you take a permutation which decomposes into n over m cycles, and you take an irreducible character, you evaluate it at this permutation, then the absolute value is bounded roughly by the degree of the character to the 1 over m. So that's a very nice result. And we have some generalizations of each, but it's too technical to mention them in detail. Now let's move from Sn to groups of Lie type. You know, someone said that the classifications is a theorem that most finite simple groups are groups of Lie type. So what can we say about them in similar contexts? So again, now the game is to find the good upper bounds on character values, and there is a very useful and classical result of David Gluck saying something like this: that if you take a non-trivial element and you take something over fq, then chi1 over q to the 1/2 is a bound, or maybe with some constant. There is another result of Gluck which is already exponential, you see, but it gives numbers which are, I'm not quoting it in its full form, but it gives numbers which are very close to 1. In a recent work with Roman Bezrukavnikov and Martin and Tiep, we get some kind of exponential bounds for groups on character values groups of Lie type. And for example, if you take if you take a matrix with 1, 1, 1, 1, and then minus 1, minus 1, minus 1, minus 1, a diagonal matrix like this in GLN, then the character bound which you get is the degree of the character, the square root of the degree of the character, which is analogous to the Formin-Lulov of bound. So there is a nice connection between bounds for Sn and bounds for GLN. But this is not the result. Is we have many assumptions here, and the centralizer should be contained in a split-Levy subgroup, etc. And there is still more to do. There are various applications of this, but then there were exciting developments later. So Bob Guralnik and Michael Larsen and Pham Thiep developed what's called a level theory of characters, and very impressive, strong new exponential bounds coming from these. And also Jay Taylor, who is here, and Pham Thiep, they managed to do what we did with split Levy, with non-split Levy, assuming there is a connected center. So there are lots of developments in this area very recently. Here is a conjecture about. You see, it's open because it's numbered. So here is a general conjecture about the mixing time for a finite simple group of Lie type and a conjugate, a non-trivial conjugacy class as a generating set, that the mixing time of the random walk is roughly log of the group order divided by log of the class size, okay, with some absolute constant. There is some history here. Essentially, this conjecture is due to Alex Lubatsky, but he conjectured. First of all, his conjecture was that in such a situation, the mixing time is bounded by a linear function of the diameter of the respective Cayley graph. Okay, so that's a very nice conjecture. Unfortunately, it's false for alternating group. If you take a n over 2 cycle, it's already the class of n over 2 cycle is already a counterexample. Also, when he conjectured it, it was in the 90s, and only later Martin and I showed that the diameter is bounded by a similar expression, log g over log c. But still, I mean, essentially, I guess it's very much related to Alex. This conjecture. There are some cases where we can prove this conjecture. For example, if in good characteristic, whether the centralizer is contained in a proper split Levy subgroup, it's true. What is a more impressive result, in my opinion, is a result from the second level paper of Bob and Michael and Thiep, that the conjecture holds whenever we have large classes. So whenever we have a conjugacy class of size, the order of g to the epsilon, then the conjecture holds. So that's very nice. Okay, so okay, number theoretic method, and somehow you appear again, Peter. So so let's see. There is a beautiful result of Peter, and he's not Peter, right? What's his first name? Dave. Okay. So Cameron, Neumann, Tig, they proved I guess it's also one of the first applications of the classification to permutation group theory, that most natural numbers, for most natural number n, every primitive subgroup of Sn is Sn or An. Now, most is in the sense of density, that if you count these numbers up to x, then it will be little o of x, okay? So the number of exceptions to this result up to x is roughly, they show is roughly twice the number of primes up to x, so it's roughly 2x over log x. And the main contribution to the nasty integers, the counterexample, are simply the primes and the prime plus 1. Well, the primes you can guess if you take a cyclic group of order p. Of course, it's primitive, and here you can take PSL2p and acting on a parabolic subgroup, so it's p plus 1. And so if you use Onan's-Scott, the proof core is counting indices of maximal subgroups with trivial core of almost simple groups. Now, there is a notion, I don't know who first introduced it, of quasi-primitive group. You know, primitive group has the property that every non-trivial normal subgroup is transitive. But you can say, okay, but if we only require this. If we only require this, we call the group quasi-primitive, and it's a genuine extension of the class of primitive groups. For example, to show that it's an extension, if you start with a group which is a finite simple group, and you let it act on cosets of any transitive action of a finite simple group is quasi-primitive, simply because if you have a non-trivial normal subgroup, then it's the whole of G, and I said that G is transitive. So there are many non-primitive and quasi-primitive groups, and in a paper with Roger Heath Brown and Cheryl Prager, we had this extension of the Cameron-Neumann-Tig result. So for most n, every quasi-primitive subgroup of Sn must be either Sn or An, and actually the number of exceptions up to x, in their case it's not, in our case it's a bit more than 2x over log x, but it is roughly 2 to the 7, 6, etc. x over log x, so it doesn't add much. And the proof core is to count indices of all, let's simplify it, let's count indices of all subgroups of finite simple groups, not necessarily maximal subgroups, indices up to x. Okay, so let me, I'm talking about number theoretic applications, so I should have mentioned it that Roger Heath Brown had a huge contribution here, and basically it's if you want to, I mean the main in both papers the main trouble is PSL2p, and but here you have to count all subgroups of indices of all subgroups of PSL2p, and this requires quite elaborate sieve methods, and Heath Brown is very good at this, but it wasn't just, you know, to quote an existing result, but to prove a new result in sieve methods. Okay, so another context where number theory was used is related to the notion of length and depth of groups. So we first defined the notion of an unrefinable chain. So you want to descend from G to 1, and all the inclusion are proper, but everything is maximal in the previous thing. Okay, maximal subgroup, not necessarily normal. So this is an unrefinable chain, and now the length of a finite group is the maximal length of an unrefinable chain, and the depth is a minimal length of an unrefinable chain. Yeah, if I wouldn't say unrefinable, that the depth of every non-trivial group would be 1, because you immediately jump from G to 1. It's not very exciting. You have to go by maximal subgroups each time. Now, there is some, first of all, clearly the depth is bounded by the length, and this is bounded by omega of the order of the group, where omega of n is a number of primes in the prime decomposition of n, where you count multiplicities. So this is a formal definition of omega. This is trivial because, you know, each time you jump, you have some prime involved here. So this is trivial, but there are already nice results here which are not trivial, and so Iwasawa proved in the 40s that the depth equals the length, which means all unrefinable chains have the same length. It's a very kind of nice condition. So this is equivalent to the group being super soluble. I must say I didn't check it. I didn't read this paper, but it should be interesting to see how he proved it. Now it is known that finite simple groups have depth at least 3 and therefore length at least 4, because otherwise they would be super soluble. And Janko was interested in finite simple groups of lengths of the minimal possible length 4. So Janko actually essentially, of course, before the classification, he managed to classify the finite simple group of length 4, and there are A5 and some group of PSL2P with certain conditions like this. And there was a natural question: are there infinitely many simple groups of length 4? This is still wide open, but an approximation to this is a theorem of Aladi, Solomon, and Turo, saying that there are infinitely many finite simple groups of length at most 20. And this required number theory, and again, yes, it's again sieve methods. And the group they constructed are PSL2P, but they had to work with to prove all kinds of things about prime factorizations of P minus 1 and P plus 1. In a more recent work with Tim Burness and Roger Heath Brown and Martin, we showed that there are infinitely many finite simple groups. Again, they are PSL2P, but their length is at most 9 instead of 20. I mean that's again, sieve methods are heavily used. The paper contains various other results, but they are not connected to number theory. And the proof is based on you know, the contribution of Roger Heath Brown, which he proved that there are infinitely many primes numbers P, such that omega of P plus 1 is at most 8, and also omega of P minus 1 is at most 8. And this led to this particular result. I should say that whenever I ask Roger Heath Brown a question, then it's always something which is unknown, but it's always something which he proves rather quickly. And I ask him questions, you know, if I have you know, group theoretic motivation. So maybe you should give me a group theoretic motivation for the twin prime conjecture. Okay. Now lengths of Sn, again, Peter Cameron, and now Solomon and Toole, it's roughly 3n/2. We don't have much time, so ignore the details, but this was a conjecture of Latzi-Babai. And what can we say about the depth of Sn? So again, number theory pops out miraculously. What happens is that we manage with Tim and Martin to prove that the depth of Sn is at most 24 for all n. You see, the length was roughly 3n/2, but this is bounded by quite a small number. And the proof uses the Vinogradov-Helfgott solution to the ternary-Goldbach conjecture that every odd number, at least 7, is a sum of 3 primes. Okay. Before Helf got the 7 was an unspecified constant. Okay. But this was an amazing work, you know, to do it for 7, and there is a whole book published by Annals of Mathematics series about it. So it's a very deep result, and the basic idea, given that this theorem is not so complicated. I mean, the idea is to gradually pass from Sn to this using the ternary Goldbach conjecture here, and the idea is that if you have SP over 1, you can pass to PSL 2 and as a maximal subgroup, and then from PSL 2 often you can pass to a bounded subgroup. Okay, and once you're in a bounded subgroup, then you are done essentially. So that's the idea, and I really put you a challenge whether I mean, this is so deep, and this looks quite a naive result. So whether you can think of you know, non-number theoretic proof of something like this. I think I promised you. You remember that algebraic geometry was in green, and I said to you that green is roughly unseen. So except from this, there is some quick introduction to word maps, but I will not do it here. And algebraic geometry, and maybe just the last slide, the summary is that it's sometimes worthwhile to go away from group theory in order to make progress in group theory. And I guess that this demonstrates the diversity of mathematics, but also its unity. Thank you for your attention.